Hello everyone, this is Professor Jimenez, and today we will design a Bargraph voltage detector which is based on the A to D converter. And right here we have the PIC 16F1619, which will be reading a voltage input, and it'll be turning on or controlling an LED bar graph with 5 levels. And in this practice we will design a 5 LED bar graph code to indicate voltage levels greater than 0.99, 1.99, 2.99, 3.99 and 4.50 volts. And if the voltage is greater than 4.5 volts, the LED on RC4, this one, will be flashing at a 10 Hertz rate. So this is the electronic schematic. RA1 or analog input 1 is where you apply a voltage using a trim pot. We have here a piezo buzzer, but we can use it later, not at this time. So the voltage levels must be established first using this truth table. In this truth table, you will see that if the input voltage is greater than 0.99, and 0.99 is based on this code, because we are working at 8 bits, so this is 20 millivolts, 40 millivolts. So it's according to the binary weight. So it's 20, 40, 80, 160, 320, and 640. So the sum of these voltages is equal to 990 millivolts. And so if we use a greater than, so that will be equal or greater than, we can say 1 volt. So in binary code is this number, so this is number 3 in BCD code, and this is number 3 in BCD code. So if we add them together, if we put them together, this is the hexadecimal code 33. And same for the other voltages. You can find the sum of this binary code and determine its respective hexadecimal code. So you can work with both codes, binary or Xcode, in the main program. The instruction we'll be using for comparison is this one. If the voltage measure is greater than the hexadecimal code, then port C in that bit, with the respective bit that we are activating, will be equal to 1. So that's the main instruction. And to generate a bar graph, we will insert 50 milliseconds pauses after every comparison, so that the eye can hold that reading, so the user can see that reading. But you can change that, the refreshing rate. And so first we have with the specs, we specify the PIC micro 1619, the voltage levels, and we declare 2 variables here. The volt is a variable byte, I is a variable byte, so we are declaring 2 variables. So we declare port A as an input, on RA0 as an input, which is A and 1, and cell A and 1. So we are declaring that port A is an input, and then as an it is declared as an analog input. So that'll be the only pin we will be using for reading the input voltage. As I said before, it's going to be here on A and 1. Okay, so if we continue with the code, we connect input our master grid to voltage internally. We clear all the latches in every port. We clear all the pull-up resistors. We don't need them. We set the frequency to 4 megahertz, and we disable the module, the comparator module based on op-amps, and we define the ADC bits. In this case is equal to 8 bits. The clock source is number 3. A sample, a hold and sample of 50 microseconds internally. So we start with this label RPT, and we clear port C equal to 0 to start with the port completely erased, completely clean or clear. So we start reading with this instruction, ADC converter input channel 1, and so we are reading channel 1. Let me check here on the, yep, it's channel 1. So we were here, we are reading channel 1. So we read AN1, let me change that, and store the voltage reading, the input voltage reading on variable volt. This is the variable where we stored this reading. And now we have to start the comparisons, the magnitude comparisons. So we ask if volt is greater than 383, which is equivalent to 0.99 volts, then turn on port C or RC0 equal to 1. So it'll turn on the first LED. If it's not true, if this condition is not true, it'll go to the next. But this will not happen, because if this is not true, the other ones will not be true. So everything will be 0, all the LEDs will be off, and it'll go to repeat. So we just start increasing the voltage, and if the voltage is greater than 1 volt, the first LED on RC0 will be on. If you keep increasing, once the first LED is turned on, it happens that the rest of the conditions will not be true, and the LED will stay on for 50 milliseconds before taking a new reading. So 50 milliseconds, it goes back, clears port C for 1 microsecond and another 10 microseconds approximately right here. And then your eye will not see that. Your eye will keep seeing the LED as a turn on, because 11 microseconds or 12 microseconds is a very brief period of time. And if the voltage is greater than 1.99 volt, let's say 2 volts, both conditions will be true, these two. So 2 LEDs will be on right now, and it'll act as a bar graph. If the user keeps increasing the voltage, now 3 conditions will be true, these 3, okay? So the LEDs will be getting activated in this sequence, in a bar graph sequence. Now in the last one, in the last comparison, a volt is greater than E8, which is 4.5 volts, then pulls RC4 at a rate of 10 hertz. So it'll go to this label, flashing LED or FLD, and it'll do 2 times this. It'll turn on RC, it'll turn off RC0, RC4, then wait 50 milliseconds and turn it on for another 50 milliseconds. So it'll do these 2 times at this rate, 50 and 50. So that's 100 milliseconds, and 100 milliseconds fits 10 times in 1 second, so that's 10 hertz. And then once it performs this function 2 times, it goes back to RPT, so this label, and it goes back to RPT. And then once it is here, it starts taking a new reading. So if the conditions are true, it'll keep flashing. So because it'll detect, okay, it's still greater than 4.5 volts, so it'll keep flashing the LED twice at a rate of 10 hertz. But once the voltage is less than 4.5, it'll turn off that LED. Okay, because right here we are turning off everything. So it'll start making more comparisons to determine which LEDs will be turned on. So it is a short code, and this code might be a little bit different from the ones you might be receiving in a microcontroller where all the practices are integrated. But I wanted to explain this in an independent format so that you can see this code free of other menus and other instructions, which happens when we integrate all the practices in a single chip. So in this case, this is just for one single chip where you might want to assemble this code. So this is how you do the wiring for the 4, or in this case 5 LEDs. We're not using that one. So, and well, this is for in case you need to make increase it to more levels. So you want to have, instead of 5 levels, you want to have 10 levels for a Bargraph voltmeter. You can do it. So you can just connect all the outputs to port C, as you can see here, right there, and then you wire the 8 LEDs, and you have to keep increasing this. So you just have to add more comparisons right here, so, and increase your table, so you will have 10 comparisons instead of 5. And this table must be it must be bigger than this one. So you have to, for example, you want to use 0.5 volt steps of comparison. So you can start here with 0.50, 0.99, 1.50, 1.99, or 2.49, 2.99, 3.49, 3.99, and so on. So, and of course, once you have the binary code, then you convert it to the X code, and you're ready to put it there. If, for example, in the binary code, if you have this code for 0.99 in binary, and we can make a copy paste from here. So if we go to the code and notice that the comparisons are made here in binary, but let me amplify this a little bit. Okay, you're doing the comparisons here in binary. You can, if you don't want to do it in, in X code, you can do them in binary code also. So the syntax is you have to use a % symbol, and then you insert the code. So let me just put it in black. Okay, so you see, and this is 0.99 volts. So if volt is greater than binary code, this binary code, which is equivalent to 33 in hexadecimal, but you can put it in binary using the % symbol preceding the binary. So, and that's another way to work with your code. Okay, even if I leave it this way and I combine X with binary with X, it'll work. It'll compile and it'll work perfectly. Okay, so this is the code, and in the next ones I will explain this in another video. We will make a Bargraph thermometer. It's very similar to this practice, but we will use a temperature sensor right here in this input, so that we can represent temperature in this Bargraph. So you do this assignment in where your assignment will be detecting voltage levels of 0.5 volts from 0 to 4.99. Okay, and so finish your table, finish this table with the new X codes, and the due date is always a week after this video is posted on the group. Okay, so thank you for your time.